Welcome students. Earlier we have studied about electric field, and now in this lecture we will study about electric field lines. Let us see some general properties of electric field lines. Now the first property is that electric field lines, they always start from positive charge and they ends at negative charge. Now the question arises, what happens if there is only a positive charge and there is no negative charge? Then if there is only positive charge, then electric field lines will emerge from the positive charge and they will move to the infinite distance. In this case, you have to consider that the negative charge is at infinite or at infinity. Similarly, if there is a negative charge, then once again we have to imagine that there is a positive charge at infinity and the field lines are coming from that infinity and they enters in negative charge or ends in a negative charge. So this is the first property. Now second property, if there is a charge free region, that means if there is no charge. Now no charge means consider that the charge is at infinity, very far away. So if the charge is at very far away, then the electric field lines will emerge from that charge and then they will move, and in a free space these field lines can be considered as a continuous curves. You can see here the field line only, there is no charge because the charge is at infinity, somewhere away. So that electric field lines are coming from that and they will move further like a curve or a straight line. Remember, if there is nothing around that charge, only one charge is there, and if that electric field lines are emerging from that positive charge suppose, then that electric field line will be straight. But if there are some other charges also around it, then these field lines can be curved also. But main important thing is that it is continuous. It cannot be a broken line. The curve is a continuous curve. Now third important property of electric field lines, it says that the field lines can never cross each other. That means if this is one field line and if this is other field line, then they will never cross in this way. No two field lines can cross each other. Means if one field line is like this, then the other field line will move from the first field line, but it will not intersect each other. Earlier also we have seen that if there is a positive charge, then the field lines will be like this. You can see here, no two field lines they intersect each other. If we consider one positive and other negative, then electric field lines they emerge from positive and end in negative. If we draw another field line, because we know that from positive charge many field lines emerges, we can say infinite number of field lines they emerge. So if the other field line is emerging from this, then it will end in the negative. If the field lines is emerging from here, then it will end like this. If other field line is there, then like this, like this, like this, and so on. But you can see that no two field lines will intersect each other. So this was the third property, that no two field lines will cross or intersect each other. Fourth point, electrostatic field lines do not form any closed loop. Now see the word electrostatic. Electrostatic means stationary charge, electric field lines due to stationary charge. So electrostatic field lines do not form any closed loop. So if we consider a positive and a negative charge, then we know that the electric field lines will emerge from positive and ends in negative in this way. So you can see here, these field lines, they do not form a closed loop. It will always emerge from positive and end in negative. Once again, from negative to positive is not possible. If it was possible, then the closed loop can be formed. But if we consider a magnet and a magnetic field lines, suppose this is north pole, this is south pole, magnetic field lines, they emerge from north and ends in south. Once again, inside the magnetic field lines are from south to north. So here, for a magnetic field lines, they form a closed loop, but electric field lines, they do not form a closed loop. Clear? So this was about the general properties of electric field lines. So now you can see in this topic in your textbook, electric field lines. Its properties are given on this page. The field lines follow some important general properties. You can see that for a positive charge, that means if Q is greater than 0, then field lines, they are coming out. And if the charge is negative, that is Q is less than 0, then the field lines are coming towards the negative charge. First property, field lines start from positive charge and ends at negative charge. And if the charge is single, then it may start or end at infinity. Second property, that the electric field lines can be taken as continuous curve without breaks. You can see here, without breaks. That means there is no cut in a curve of electric field line. Third property is that the two field lines they never cross or never intersect each other. And last and fourth property is that electrostatic field lines they never form a closed loops. But remember, magnetic field lines they form a closed loop. And here one thing we have to remember that it is for a static charge. Electrostatic word is used. So if the charges are stationary, then their field lines they will not form a closed loop. You can see the same thing here, that no two field lines they intersect or cross each other. They start from positive only. Here you can see both the charges are positive, so they are starting from the positive. But if one is positive and the other is negative, then it will start from positive and end in negative. You can see here also it will start from the positive and then it will end in negative. So these are about the field lines. Let us see a video which explains electric field lines.
Electric field lines. Michael Faraday, 1791 to 1867, introduced the idea of lines of forces. Electric field lines. Field lines give us a means of representing the electric field pictorially. The electric field vector E is tangent to the electric field line at each point. The line has a direction that is the same as that of the electric field vector. The number of lines per unit area through a surface perpendicular to the lines is proportional to the magnitude of the electric field in that region. Electric field lines. General. The density of lines through surface A is greater than through surface B. The magnitude of the electric field is greater on surface A than B. The lines at different locations point in different directions. This indicates the field is non-uniform. Electric field lines. Positive point charge. The field lines radiate outward in all directions. In 3 dimensions, the distribution is spherical. The lines are directed away from the source charge. The positive test charge would be repelled away from the positive source charge. Electric field lines. Negative point charge. The field lines radiate inward in all directions. The lines are directed toward the source charge. The positive test charge would be attracted toward the negative source charge. Electric field lines. Dipole. The charges are equal and opposite. The number of field lines leaving the positive charge equals the number of lines terminating on the negative charge. Electric field lines. Like charges. The charges are equal and positive. The same number of lines leave each charge since they are equal in magnitude. At a great distance, the field is approximately equal to that of a single charge of 2q. Electric field lines. The positive charge is twice the magnitude of the negative charge. 2 lines leave the positive charge for each line that terminates on the negative charge. At a great distance, the field would be approximately the same as that due to a single charge of positive q. Electric field lines. Rules for drawing. The lines must begin on a positive charge and terminate on a negative charge. In the case of an excess of one type of charge, some lines will begin or end infinitely far away. The number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. No two field lines can cross.
Now let us move to our next topic. Topic number 1.10, electric flux. Consider the electric fields moving from left to right. Now in this electric field, if I put a surface, suppose a plain paper, now we know that this surface has some area. So these electric field lines are linked with this area. Let us denote the area by S, and as we know that area is a vector quantity, so I'll write here as vector S. Now these electric field lines are passing through this plane surface, so we can say that this electric field is linked with the surface area. So now we can define electric flux as phi is equal to electric field dot surface area. Now why it is a dot product? Because if we rotate the surface in an electric field, then angle may change. In one particular case, if the surface is exactly perpendicular to the electric field, then the angle will be 0. Why angle is 0? It is because the area is always perpendicular to the surface, like this. Suppose if you consider the surface of this page, then the area vector of this surface is perpendicular. But if I rotate this surface, then the angle will change, and if the angle changes, then the flux also changes, and that's why it is a dot product. And we know that if we remove the dot product, then it will be E S cos theta. Now here we have considered the whole surface, but if we consider the small part of the surface, suppose only this much part, then electric field line passes through it, and if we have taken the small part, then we can take this surface as delta S. So in this case we can write now flux passing through this much part, that is delta phi, is equal to E dot delta S. So suppose now electric field is in this direction, which is shown here. If I put my hand like this, then you can see here this electric field is passing through my hand, that means surface of my hand. So in this case maximum electric field passes, and so the area vector, that is, if this is the surface, then area vector is also like this, in this direction. Electric field and area both are in same direction, so angle is 0. And if the angle is 0, then es cos 0 is 1. So finally we can say that the flux is E into S. But if I say electric field is in this direction, but if I'll rotate my hand like this, so now the area vector will be in this direction, it will be in this direction. Electric field is in this direction, area vector is in this direction. So now the angle between electric field and area vector is 90. So in that case ES cos angle is 90, so cos 90 is 0. So flux phi is equal to ES into 0 is equal to 0. So we can say that the flux can be maximum or it can be 0 depending upon this angle. Now electric flux, see in your textbook, the plane surface is given here. You can say this is the plane surface denoted by delta S. Now see, earlier also I have told you that the bold letters, they represent the vector. Means here delta S is a vector quantity. So this is the surface. It is placed inside the electric field denoted by capital E. So in this case, if the surface is exactly perpendicular, that is normal to the electric field, then the area vector of this surface will be in the direction of electric field. Means electric field E and delta S, that is surface, both are in same direction. In that case the flux will be maximum, because all the electric field lines will pass through the surface. But if we will rotate the surface with some angle, then some of the components of electric field lines will not pass through the surface. We know that for any vector there are two perpendicular components. So here also you can see here this surface is rotated by some angle. So now the area vector is in this direction and electric field is as usual, which is in this direction. So there is some angle theta. So now if this surface is rotated, then flux goes on decreasing. And if the surface is made parallel to the electric field, means electric field is in this direction and the area vector of the surface will be perpendicular. In that case, no flux is linked with the surface. So finally, as this electric field and surface, they are related by the angle theta, and that's why the formula for the flux is the dot product of electric field and surface. And we know that if we remove the dot product, then we have to put a cos theta. Now sometimes the surface cannot be a plane surface like this. It can be a curved surface also. So in that case, we have to consider a small element which is shown here. And then we can calculate the flux. Now let us see a video which explains electric flux.
Electric flux. The electric flux through a surface held inside an electric field represents the total number of electric lines of force crossing the surface in a direction normal to the surface. Electric flux is a scalar quantity and is denoted by phi. Consider flow of a liquid with velocity v through a small flat surface ds in a direction normal to the surface. The rate of flow of liquid is given by the volume crossing the area per unit time v ds and represents the flux of liquid flowing across the plane. If the normal to the surface is not parallel to the direction of flow of liquid, that is, to v bar, but makes an angle theta with it, the projected area in a plane perpendicular to v is v ds cos theta. Therefore, the flux going out of the surface ds is v bar dot n cap ds. For the case of the electric field, we define an analogous quantity and call it electric flux. We should, however, note that there is no flow of a physically observable quantity, unlike the case of liquid flow. In the picture of electric field lines described above, we saw that the number of field lines crossing a unit area placed normal to the field at a point is a measure of the strength of electric field at that point. This means that if we place a small planar element of area delta S normal to E bar at a point, the number of field lines crossing it is proportional to E delta S. Now suppose we tilt the area element by angle theta. Clearly, the number of field lines crossing the area element will be smaller. The projection of the area element normal to E is delta S cos theta. Thus, the number of field lines crossing delta S is proportional to E delta S cos theta. When theta equals to 90 degrees, field lines will be parallel to delta S and will not cross it at all. Thus, the area element vector delta S bar at a point on a closed surface equals delta S n cap, where delta S is the magnitude of the area element and n cap is a unit vector in the direction of outward normal at that point. We now come to the definition of electric flux. The electric flux delta phi through an area element delta S bar is defined by delta phi equals to E bar dot delta S bar equals to E delta S cos theta, equation 1, which, as seen before, is proportional to the number of field lines cutting the area element. The angle theta here is the angle between E bar and delta S bar. For a closed surface, with the convention stated already, theta is the angle between E bar and the outward normal to the area element. Notice we could look at the expression E delta S cos theta in two ways. E delta S cos theta, that is, E times the projection of area normal to E bar, or E perpendicular to delta S, that is, component of E bar along the normal to the area element times the magnitude of the area element. The unit of electric flux is Newton meters square per coulomb. The basic definition of electric flux given by equation 1 can be used in principle to calculate the total flux through any given surface. All we have to do is to divide the surface into small area elements, calculate the flux at each element and add them up. Thus, the total flux phi through a surface S is phi approximately sigma E bar dot delta S bar equals to sigma E bar dot delta S bar, equation 2. The approximation sign is put because the electric field E bar is taken to be constant over the small area element. This is mathematically exact only when you take the limit delta S tends to 0 and the sum in equation 2 is written as an integral.